Всем привет! Спасибо, что пришли. Меня зовут Филипп. Я прихожу из Хорватии. Я работаю в команде андроидов в агенции Five. And that's pretty much it. Everything I can say in Russian. So about me, as I said, I'm an Android developer at the Five agency in Croatia. I'm also an Android author and tech editor for the Ray Wenderlich publication, which is really big in the US. And I generally love everything about speaking, mentoring, writing, so teaching, pretty much any place I can share my knowledge. So this is why I'm here. As mentioned, I'll be talking about the Kotlin Coroutines API. The full talk name is Deep Diving into the API. So I'll try to go through the entirety of the API, through all the constructs, all the little concepts that you may have seen but not understood correctly. And the flow today would be to just have a brief history lesson about the asynchronous programming we had so far, then introduce coroutines and their solutions for working with asynchronous code, and suspending functions, a special mechanism the coroutines rely on. And I'll try to go through the inner works, so some of the things you may not really understand, or at least what I didn't understand when I started learning about coroutines. And finally, I'll try to talk a bit about writing quality code with coroutines, or rather in general when it comes to concurrency. So if you look back to the days of DOS, we had like a single core processor, and pretty much all we could do is operate with one thread, which means that if you try to run multiple tasks, that wouldn't really work, and you could only do one thing at a time, which kind of gave you the idea that you had to wait a lot to switch to something else. But nowadays, as hardware and software are improved on a daily basis, we get more and more power and more opportunities to work with concurrency. And for example, if you look at this image here, this little pop-up, while we're downloading something for the application, we might be doing some synchronization in the background, and in a different thread, we may be doing some statistics or maybe some computation which is not related to the downloading. And of course, we're updating the UI on the UI thread, so there's a lot of things going on here, and all this revolves around concurrency. So in Android, what we usually do is we either use callbacks, for example, in Retrofit, when you use the networking library, you use callbacks to communicate between threads, or you use Rx to have streams of data which you transform, which you map to different results, maybe filter out, and you use the schedulers to switch between threading. And all this works with concurrency, as I've said, and all these concepts haven't really changed in the past 10, 20 years. So it's funny to me when people say, what is this black magic, when they try to learn coroutines, what is it? So how does it work? People usually have the idea that it's just a bunch of magical things that happen in the background and you can't really grasp it. You can't really understand what it is. But my idea today is to kind of demystify coroutines for you and explain it really simply and one step at a time, so you can understand the entirety of the API. Okay, so in general, to learn about coroutines, you first have to know how to build them, which makes sense. So you do this with special functions, which are called coroutine builders. But then again, when you start building coroutines, you get this concept of suspending functions. So you have to learn about that as well. And furthermore, suspending functions work based on continuations, continuation constructs, and suspension points as well. So you have to learn about that. And once you get a grasp of all this theoretical knowledge, you start digging more thoroughly, and you get to the coroutine scope to which you bind the coroutines. And then again, the coroutine scope kind of works with the coroutine context elements. So you pretty much get to this point where you're looking at the entirety of the API, and you're like, what is happening here? So what is each of the components, and how do I get my head around this? And it surely is a lot, but I'll try to go through a simple process, simple flow, which I use to understand coroutines and which has helped me a lot. So of course, let's start with coroutine builders. a very simple builder, or the one you'd usually use, is the launch function. So you use the launch function, and within it you get a lambda, which will be executed in the coroutine. So for example, it should print this is a coroutine in a different thread or a different coroutine, right? But it's not that simple. So when you look at the definition of the launch function, first thing you get that is an extension function on the coroutine scope interface. What this means is you have to launch coroutines, or you have to bind them to some kind of a coroutine scope, which is basically the life cycle of coroutines. We'll talk about that a bit more later. And then you get the the coroutine context, which is like the definition and like the internal works of the coroutines, which you start. And by default, it's the empty coroutine context, so it doesn't really do a lot. It just launches a coroutine in a simple way. Then you have the start, the coroutine start parameter, which dictates if your coroutine will be launched immediately after calling the launch function, or if it will be started lazily, so when you say explicitly start this coroutine. And finally, like the most important thing you would use is the coroutine scope extension parameter type extension function, which is called the block. So this is the block of code which gets executed in a different function. But this launch block returns something called a job. So to fully understand what a coroutine is, we have to go through the job definition and what the job is. So usually we're used to having jobs that earn us money and get us trips to these lovely conferences. But in coroutines, jobs are just simply cancelable pieces of work. So when you launch a coroutine, you get a job which you can cancel. So once you cancel the job, obviously the coroutine will be stopped. And to be able to stop and resume at certain points in time, it has to have some sort of life cycle. So we'll go over that in a slide. And finally, you can create relations with your job. So you can create a job and then create another coroutine within the job, which kind of creates a relation between them. So if the topmost job, the parent job, gets canceled, the children get canceled as well. Meaning you can build multiple requests with different hierarchies, and you can just cancel the topmost job, canceling all of the work. So when you start the job, more or less, unless you've used the lazy coroutine start, it gets started immediately. And if it completes in a good way, nothing wrong happens. It will go into the completing state, and finally in the finish state. But that's not really true. So as I mentioned, there's a parent-child job hierarchy. So in the completing state, the job actually waits for all its children. So if you used a job to be a parent, all of its children have to finish as well for the job to finish entirely. So it means that if either the job itself, like the parent job, or any of its children are canceled by you, or they fail with an exception, the entire hierarchy of the jobs, or the tree of jobs, will be canceled as well. And furthermore, it will go into the cancelled state where it finishes in the end. So all this lifecycle is bound to something called the coroutine scope, as I mentioned. And it's a really good thing that it works this way, because it allows you to do really smart cancellation and really clean code, so you don't have to worry about wasting resources, and we'll get to that in a bit. So if I go back to this example, this isn't really true, because you can't really just launch a coroutine out of nowhere, so you have to bind it to a certain scope. So this is more like it. We use the global scope instance to launch a coroutine. Now, you wouldn't usually do this, because the global scope is the coroutine scope that's bound to your application. So as long as your application is alive, it will be running. So for example, if you're in an Android app and you've started some image download on some detail screen, for example, you go back from that screen, so you leave that screen. If you launched a coroutine in the global scope, it will keep on running, which is a waste of resources. So you should always try to build your own scopes for certain parts of the application. You should try to bind it to something that has a really steady and explicit lifecycle. For example, like the presenters, if you have presenters, or view models, if you have view models in Android. You can simply extend the coroutine scope interface, and you have to do something to fulfill the contract. So you have to provide the coroutine context value. But what's cool now is that since the base presenter is a coroutine scope in its essence, you can simply expose a function called onDestroy here, which will cancel that scope. So whenever you leave a screen, you can just simply call onDestroy. The scope will get canceled, and all of the coroutines within that scope will be canceled as well. So you can clean up your resources very easily. And now, anywhere in the presenter, you can actually use the launch function to launch coroutines. So I've been talking about this context for a bit, and you're probably thinking something like this. So not another scope, sorry, not another context you have to handle. We have the Android context, which is pretty hard to handle it by itself. And a lot of bugs are introduced because of that. But it's not actually an Android context. It's a bit different, although it kind of serves the same purpose. So the coroutine context is just a set of a bunch of elements which define the way the coroutines are executed or the coroutines behave. So we have each of the elements like play a specific role in the coroutine. For example, we have the context elements for lifecycle, for threading, and for exception handling, which means that if you combine all three, you get a coroutine which has a steady lifecycle. For example, it handles the cancellation with your screen. You can switch threading between the main thread and the background thread for expensive tasks, and then push back to the main thread to display some result. And of course, you can handle the exceptions that happen within your coroutines. So if we go back to this snippet, here I provided in the base presenter the coroutine context instance by returning the dispatcher's default context combined with the parent job context. So what this does is it says that every single coroutine which is launched by default in my base presenter will be launched using the dispatcher's default instance, which just simply pushes it back into a thread pool of workers. So this will mean that all of the coroutines by default will be in the background thread. If I want to push the results to the main thread, I have to simply use the dispatcher's main in the coroutine context or the launch block. And furthermore, I combine it with the parent job context. So whenever I create or recreate and cancel the parent job, all of the coroutines within will be canceled as well. So I have free cancellation and free threading here just by using 2 lines of code. When you look at the actual definition of the context, it's pretty abstract, just like the Android context. So this doesn't really tell you much. It says that there's a bunch of elements and that you can get those elements using certain keys, but how do you actually find contexts and where do you find them? Which ones should you use? So as you can see, the job interface, or rather the job construct, implements the context interface. So you can use jobs to govern the lifecycle part of the context. You can use the continuation interceptors, which are actually the dispatchers I mentioned before, which simply govern threading. And finally, you have the coroutine exception handlers, which are pretty self-explanatory, so they handle exceptions. So let's see how the elements are handled. For example, the continuation interceptors, which interceptors are there or which dispatchers are there? We have 4 here listed, but more or less you'd use only 3 of them. So they handle the internal threading by switching threads between coroutines. You have the main dispatcher, which is obviously for the main thread, for the UI thread, for any UI work you have. You have the I/O dispatcher, which is used for, or should be used for, anything that's related to expensive calls, like network requests, writing to the database, maybe reading some files, things like that. You have the unconfined dispatcher, which is similar to the trampoline scheduler in RX. So basically, it forces the coroutine to run in the thread it was called in. So it's useful for testing, but in your code, in your business logic code, you wouldn't really use it. And then there's the default, obviously, which pushes the coroutine in the background thread. And it's pretty much a relay for executions flow. So once you start a coroutine, you say use the default context or the I/O dispatcher, and it will just switch to the thread you want it to, and then you can switch back using the same class or same instances. So for example, here I have a expensive call. I launch a coroutine on the dispatcher's IO thread, or the dispatcher's IO context instance, whichever you want to call it, and it goes back into the background thread, which is used for heavy work. I get the result from a blocking function called getExpensiveResult, and then after I get the result, I just simply launch back to the main thread and I say update UI with the result. So this is pretty much what you have to do to handle some heavy work in the background and then update the UI. It doesn't take a lot of code, and it doesn't take a bunch of callbacks or a bunch of RX complications to do this. So yeah, the exception handler. The title was wrong. Yeah, the exception handler, they basically handle exceptions within coroutines, which means that once you provide an exception handler, a custom exception handler, when the coroutine is killed by either an exception or is canceled, you can take the context you started it in, and you can restart it or you can start a new coroutine depending on the result. So for example here, a simple example, I create a coroutine using the launch function, and I pass in the exception handler. And if you look at the code, you see that it receives a coroutine context that you use for the coroutine and a throwable that happens. So you can print the context, and you can check some. You can do some checks with the throwable to see what happened. And you can print the result if, for example, this is an illegal argument exception I sent. The fun thing about this is, even though I launched the coroutine in the main function and I immediately threw an exception, the program will still run. So the while true loop will keep on looping. I won't really crash the main function here. I'll simply crash the coroutine, but the exception will be propagated to me through the handler, so I can do anything I want with the result. So coroutines in that way are pretty safe, that if something happens in the coroutine, it doesn't crash the rest of your program. It just crashes, or rather cancels the coroutine, and then you can handle the exception any way you want. Okay, so let's go back a bit. As I was saying, all of this works around suspension functions. We kind of have to know what is the difference between a regular function and a coroutine or a suspension function. So a definition of suspension functions would be that they are functions which don't really have a linear flow of execution. So usually when you launch a function or call a function, it starts and then it goes all the way to the finish line, and then it returns something, right? If something bad happens in between, like an exception, then it will break, obviously, and go back. But with suspension functions, you pretty much can stop at any point in time and as many times as you want, and then pause the function for a bit. For example, if you have a long-running operation of downloading an image, you can pause the entire function at 20% of execution, for example, and then you can resume, let's say, 10 minutes after you get more resources to download the rest of the image. So you can pause it and resume it at any point in time. This is called the process of suspension, which is why they're called suspension functions. And they rely on something called continuation constructs, which I'll go over in a bit as well. And the way they are differentiated in the code or in the system is by the suspend modifier, which kind of changes the bytecode generated. So to understand it, I generated some bytecode here. If I have a function called print some data, which simply takes some data and prints it, the Java bytecode which would be generated is something like this. So once we decompile it, we get a null check, obviously, because of Kotlin, and we'd call system.out.println with that data. That's pretty self-explanatory, so nothing special. But once we add the suspend modifier, we get some changes here. So now, going back from this, just a second. Okay, wrong one. Wait, okay. So this first function didn't return anything. It returned void, actually. So if we go forward to this, it returns an object now. And also there's another parameter here called continuation, which is named var1. So what it does here is it adds another continuation to the function. So we can understand the execution flow of the function. So if we should break something or go back, or if we should handle the execution on a different thread. But this doesn't change a lot, so let's try to add something new. Let's try to add a new delay function, which is also a suspend function. It simply delays the coroutine by 100 milliseconds in this example. And you'd probably expect that the code would be pretty similar to the previous example, right? But it's actually not. So there's a lot of code generated here. And this looks kind of ugly, so I split it up in a few slides. What happens here is the definition is same as the method definition is the same as when I added the suspend modifier, but the code itself has changed quite drastically. So what it does here is it creates a new continuation object. It tries to see if it already exists, and if it does, it just returns that continuation, or rather just assigns that continuation to this object. If not, it creates a new one. Within that continuation, we store the result of the function, and we store a label, which is used then later on to check what happens in the code. Within that continuation, we simply return the function call of the same function. So it might seem as though we're calling the same function from within, but on the compiler level, the system level, it doesn't happen like that. So it doesn't create multiple stack entries. It just simply goes back to that function with different data. In this case, it doesn't pass any data as the first parameter, the data parameter, but it does pass the continuation in which we now hold the data. So it goes back to the rest of the code once it called the same function, and it checks the label for the continuation. What happens here is if we're on this zeroth index, zeroth label, we know, or rather the compiler knows, that we're at the first execution flow of our function, which is the delay function call. What it does here is it simply delays the function and calls delay with this continuation, and then it pushes the label to 1. So it can return back to the same function again later on and go through the same case. So it goes through the same case and it says, okay, the label is now 1. I need to get the data from the function and just continue with my code. And in the rest of the code, it just prints out the data. So you can think of the continuation and the suspending functions like a state machine. So it has different states for every single suspension function call in the function. And every single time you reach another suspension function call, you change the state of the state machine. And then it moves on to the rest of the code. So basically, it takes one single execution flow, one single entry, stack entry, and it splits it up in different execution flows, like different branches. And then it just picks the branch it needs to go to. So what happens when you do something more complex? For example, we add an async await call, which we'll go through a bit later on as well. More or less, the compiler gets... Yeah, the compiler simply breaks, and it generates a huge amount of these staircases. And you know, this might be motivational, but this is just not the case for the staircase we've seen. So why does it happen? So why does the compiler break that badly, and we get the huge nested callback piece of code? This is actually an issue in the compiler. So JetBrains has opened this issue. And what happens here is that the Java compiler doesn't really know how to compile the async await call. And because of that, it generates a huge amount of nonsense, as you can see. But in reality, what it does is simply do a few state machine calls, and it switches the label again, going back to the suspension point we created using the await call, and it simply passes the data there, which you can use later on. And all this is done through the concept of suspension points. So if I paste the image of the code here, you can see these little two icons next to the code. So next to the delay function and the await function. These are called suspension points, and the compiler will actually recognize that for you. And the compiler will tell you that at these points in the code, you will be suspended, or the function will be suspended. So what happens here is you have the delay function call, the compiler suspends the function, or rather the program suspends the function. After 100 milliseconds, it goes back. Through that state machine, it knows that it received some data and that it should print it. Then it goes on and reaches this something block, which is the async block, sorry. And later on, it calls something.await. So it knows that it should compile this value using the async block somewhere asynchronously. It suspends the function again. And once the value is ready, in this case, it will return immediately because this is a simple call to get a string. But once the value is ready, it will go back to this code, to this line of code, and it will continue using, you can use that result. So this is why when we had this snippet of code and we added the delay function call, we get this huge block, which is the state machine block, which just simply checks for the case or the label of the continuation so we can know where in code we should return after this suspension has finished. So what are these continuation constructs? So what are they used for and how do they work? Well, continuations are actually like low-level callbacks. Quite in fact, they already exist in the system, and the system uses continuations to know when a function finishes in the stack, where it should go back. And it's already there, but not a lot of languages use them. So Kotlin used these continuations to implement coroutines in the language itself. So it allows you to handle continuations at a first-class level, so you can handle them manually. They hold the program state, which means that you can use state machine protocols on them. You can switch between the state and the labels. And how it looks in like the stack entries, for example, when you start a main function anywhere in the process, so when you run your program, you get the process continuation passed down to the main function. This means that if the main function returns, the process continuation will get its result. For example, if you're running a C program, something like that, you put the int main function in the code. It returns, for example, 0 if everything went well, -1 if something was broken, right? And the process can handle that. So the process knows the function returns something to the process continuation, and it can use that number, integer, to check for the result. What happens when you call a different function is that the process continuation is held within the main function, but the now called getUser function receives the main continuation from the main function. It knows about the state in the main continuation. It also knows about the parameters it got, and it knows about the return type it should return. So once the getUser function returns, it will pass the value down to the main continuation, and the main function can resume. If the getUser function crashes, so if an exception is thrown, it will be propagated all the way down to the process, and the process can handle that exception. But when you call a suspension function, something different, kind of different happens. The getUser function has the main continuation still, but the new, now called API call function, which is a suspend function, holds both a getUser continuation to go back in the stack, but also a new suspension continuation, which allows it to traverse the suspension points and the function itself. So, for example, if within the API call function we have a delay operator, it can use the suspend continuation to simply go back after that delay. And if something bad happens, it can go back all the way down through the getUser continuation to the main continuation and the process continuation in the end. Additionally, if the suspension returns some value, it will pass it down through the suspension continuation, which will in turn go all the way back to the getUser continuation. So you can return that value to a different function, even though it may be from a different thread. So, excuse me. Okay, so if you check it here, normal functions have only one continuations for the previous function, so they can go back. But suspension functions have two per suspension function call. So they can know how to navigate between them, and so they can navigate back. And continuations are actually cascades. So as I mentioned, if you throw an exception somewhere in the continuation, any continuation, it will go all the way down to the process. And in the same way, if you return a value through the continuation somewhere above the stack, for example, in a suspension function, it can be propagated all the way down to the calling function as well, depending on your code, of course. They don't create multiple stack entries, so this would probably seem that if you have multiple suspension function calls and multiple suspension points, you would create a lot of stack entries, which will in turn overflow the memory. But that's not really it. So what they do is they use a single stack entry, but they use like low-level state machines to switch between execution flows, as I've shown before. So it's not really any overhead, but it's really useful because you can do many amazing things with simple, threading control. So all of this is the theory behind coroutines, and it does seem like a lot, but in turn it's just a bunch of simple concepts, a bunch of small, simple concepts, but they are grouped together, so you have to kind of go through them one step at a time. And let's go back to Android. So in Android, you would probably use callbacks and RX, as I mentioned, and these mechanisms are used to share values between threads, right? The problem with that is if you use a lot of callbacks, you eventually get the callback hell, right? And if you try to use RX, or if you use RX, you can get to a point where it's too complex to just return a value from something. You have to wrap everything in a lot of RX constructs for some reason, or no reason, because you want everything to be RX driven. But there are different ways, through history to share values. The most simple way is, and the easiest way is to share data, of course. So you use a single point in memory, which you communicate the data through different threads. So like a single piece of data which you change and then read from a different thread and so on and so forth. This is cool, this is simple, but it's really volatile because you get race conditions here, so you can't really synchronize this in a nice way. And even if you do, you still are not entirely sure what's going to happen. For this reason, there are mechanisms like queues and other different polling, push and pull mechanisms. They are cool as well. They allow you to synchronize in a real nice way by sending events of data or bytes of data which you constantly read or write. But they can be complex in a way that you may come to a point where you have to write them in a good way, so they don't constantly block by polling for the data when it's not there, or they don't constantly send data when there's no one to listen for it, so no one to consume it, so the data doesn't go and get wasted. Then you have futures and promises in different languages, of course. There are also cool mechanisms which are rather simple. They're real good, they're safe. They can be used easily to synchronize stuff, but they can scale bad. So if you use promises, for example, you can also get into the callback hell approach, because you have to nest new promises, new calls within the existing promises, and then it can turn into a bit of a callback hell. Or you can just call promise all, but then if you have dependent promises, then you have to synchronize them in some way, or rather pass the data in some way. Whereas with futures, they're pretty simple to use, but if you have a lot of functions and a lot of mapping between them, a lot of dependencies between the calls, then you can get the callback hell as well, and you can get to really complex code. Which is why in coroutines you have something called the async await construct. Quite simply, it's it's an asynchronous construct which can return values. So you can think of it like a coroutine which has some result, a job which has some result. So the idea is to make the syntax as clean as possible, as we've seen before, and to make it understandable, but at the same time allowing you to do things like thread synchronization, like returning values from different threads, parallel codes, execution, and things like that. And of course, they rely on coroutines. So the way you would use an async block is this. So you would launch a coroutine. Within it, you can call the async block and pass in a function call which will return you the result. So going back to the expensive result I mentioned before, we now wrapped it in an async block, and we can get it in this way. The async block will be launched, the data will be compiled in the back, but we need to wait for it. And this is not actually the expensive result we wanted, for example, a user or an image downloaded from the internet, but it's actually a deferred type of the user or the image. So deferred is just a type of coroutine which is not yet compiled or not yet consumed. So to consume the result, you have to call the result deferred here, .await. Once you call the await function, it will suspend just like before, and it will wait for that result. The fun thing about this is if you launch this in on the main thread, so if the launch block was run on the main thread, the async block in the default thread, and you call the await, it wouldn't block the main thread. It would rather suspend the coroutine, and once the result is ready on the background thread, you can simply return back to the main thread and consume that result. So this is similar to futures in the syntax as you call await or get or not future, things like that, but the real power of coroutines or async await block here is that it doesn't actually block the thread, it just suspends the coroutine until the result is ready. You can just go and print the result after it's compiled. If you look at the definition itself, there's a lot of it, so there's a lot of things going on here, but it's pretty similar to other coroutine functions we've seen. So for example, it takes in the context it will run in, the start as well, so it can be default, eagerly started, or it can be lazy. You also get the coroutine scope function, which can return a value. And within the async block, you can launch new coroutines as well. What it does in the end is returns a deferred coroutine, which will hold that result, and it just returns that coroutine. So once you do this, once you call an async block, it will create a new coroutine which will hold the result within for you. So it will be ready somewhere along the lines. And this is all fine, but what about the things I've said? So like using parallel code execution. So how would you do that with async await? Well, quite simply, you would just get two async blocks. So this here is an example where you launch a async block which gets the expensive result, for example, and then you also need a user to combine that result with. So you call the async block with the getUser function as well, and what it does here is it prepares two coroutines, two deferred types. It returns them immediately, but the code within the async blocks gets launched immediately. So these two functions run in parallel, but they are not blocking the threads, or they are not using the same threads to execute. Once you get to the print results function and you await for both of the results, you say, okay, now I need both of the results. You can suspend until both of them are ready. So once again, this doesn't block any thread. This just simply suspends the function or the launch block here, the coroutine here, and once both of the results are ready, it will pass those results to the different function, and you can achieve parallel code using this. So this sounds like too good to be true, at least it did for me. So what about safety in coroutines? Can you write bad code? Can you waste resources? Can you do things that can crash your program? So as mentioned before, there's a lot of safety mechanism regarding cancellation and just not leaking resources. And for example, if you have this, as I mentioned, if this gets expensive result call, takes 10 seconds to execute, to finish. But after 50 milliseconds, we call launch on the launch block. We call cancel on the launch block. What will happen is the async block will be suspended. The function call will be suspended. We'll get the signal to cancel the coroutine, and it will be canceled immediately. So we don't have to wait 10 seconds for the entire function call to finish, or rather to be canceled. It can be done immediately. For example, in Android, if you use things like the Work Manager, the problem with Work Manager is that once you start it, it's pretty much there. So you can try to cancel it, but if it started, for example, downloading the file for 10 seconds, you had to wait 10 seconds. But what the Android team now did with Work Manager is they built a coroutine Work Manager, something like that, or continuation Work Manager, not entirely sure. But what it does is it revolves around using coroutines, and any work you start with it, once you call cancel, can be canceled immediately, so you don't have to wait those 10 seconds to cancel some work. And what you can do with coroutines is something like this. So if you call this function within a coroutine, which seemingly does a while loop and then returns some value, but it doesn't really write because the sum condition is not checked or changed. We don't break the while loop. It just loops continuously, right? Previously, in earlier versions of coroutines, if you put this in an async block or something like that, and you awaited for the result, it would suspend indefinitely, and you would leave hanging coroutines in your code. So you would waste resources. But as I mentioned, using the coroutine scope and something called structured and explicit code, the JetBrains team has made a huge effort to make coroutines as simple as possible to use and as safe to use. So now using those coroutine scopes and cancellation on jobs and things like that, you can't really write code which will break the coroutine, but you can still write bad code, right? So the idea is to write clear and expressive code. For example, if you have functions which are just fire and forget, which are just do this thing, for example, shoot some analytics or upload an image, but I don't need the result, then obviously you won't use the async block because it returns some result. So you should try to be explicit about your usage of coroutines. So for every piece of work which doesn't require a result, use the launch block. Otherwise, if you need a result from a coroutine, then use the async block and things like that. And also try to combine your context and your coroutine scopes in a way that it makes sense regarding your lifecycle in the application. Also, you can rely on things like the isActive flag in jobs. So if you do have to run for loops, or rather while loops, which shouldn't seemingly end, in coroutines, which is pretty safe, then it's better to use while isActive rather than while true loops, because then you can cancel the job and be sure that nothing got leaked, even though it shouldn't leak at all. And you should try to use finite coroutine scopes, so avoid using the global scope unless you really need to launch something and forget about it. Try to rely on your fixed mechanisms in your code. For example, in Android, these are activities or fragments. And the fun thing about this is you don't have to know about everything. So you don't have to know about all this theory I've given you, but it's really good to know it because then you would understand the coroutines much deeply, and you will have much more, have a much easier time using them. But to start using coroutines and all that, it's not really complicated. JetBrains and the Android team have gone through, a lot of things to just make it really simple to use and really safe to use on Android. To sum it up, coroutines are really nice in a way that they use pre-existing thread pools and low-level callbacks on the system level, so they don't really bring any overhead to the code. They don't really block threads, they just suspend functions, so you don't have to worry about blocking something. They're safe and clean in that way as well. And they navigate using the continuation constructs and using a set of elements you predefined for yourself, for your use case. You can really decorate them in a way that they will work for you in every way possible. So you can change this according to your needs, and you don't have to use the default stuff if you need to do something more complex. And I haven't, they're very safe and clean, as I've said, and you can still write crappy code within them, but it shouldn't really leak any resources. They shouldn't be unsafe to use. So to intercept one of the questions, if there are any questions, should you use coroutines? Well, the simple answer is if it makes sense. So you shouldn't try to push coroutines in your code just for the fun of it. So, coroutines are cool, I'm going to use them. No, you should try to see if it makes sense for you. If you have like a lot of requests, a lot of simple networking requests, which may be better off with coroutines rather than RX. And you should also see if you have some, data computation which could use the async blocks other than RX streams or maybe callbacks. Then it makes sense to use coroutines, and yeah, you should try them. I kind of encourage you to try them. But this doesn't mean that you should take your RX-driven code base and then rewrite it completely in coroutines, just like because you read some article that says that you should. It's just a matter of do you have a need for them, and if they make more sense in your code rather than other mechanisms. So some of the resources you can use to learn about coroutines. I have a few GitHub projects which use coroutines. One of these is the Coroutines Expo tutorial workshop. I'm really bad at naming. So this project I used for a different conference where I built a small app, or rather migrated some of the callback mechanisms to coroutines to show people how you can do that. And you can also use this book, which I have to kind of brag about, which Nishant and I wrote for the Ray Wenderlich team. It came out 2 or 3 weeks ago, something like that. And more or less every single bit of theory and every single bit of application we could find and we could relate to, we used to push into this book and give you examples to get a better understanding of Kotlin coroutines. Both in Kotlin, like clean Kotlin, and both on Android, like different platforms. So, are there any questions? Thank you.
Спасибо. Questions?
Questions? Okay, so this might entice you. I have one of the copies of the book here, and I have a couple of digital codes for the book as well. So if you don't have any questions now, you can reach out to me in the discussion zone and around the conference, and you can ask those questions then. And then I'll try to decide which of the questions were really cool to me, and I'll give the books away. So any questions now? Okay. No?
Yeah.
Thank you for speaking. And so many people tell me about the coroutines like lightweight threads, but I don't understand actually what is this. Can you explain it, please, on low level maybe?
So coroutines in?
And like lightweight threads.
Oh, lightweight threads. Okay, so that's a common thing to explain coroutines as. Lightweight threads means basically they don't really take up as much memory, so they don't really allocate new threads or new stack entries or anything that would bring more overhead to your code. What they do is they have predefined thread pools for threads, so you don't have to allocate anything new. You just use those thread pools to go and say which thread should execute which coroutine. And for example, if you launch, as many examples do, 1 million coroutines, 1 million launch blocks, they wouldn't allocate 1 million threads or 1 million stack entries. What they do instead is they use the fixed thread pool. For example, I think it's about 5 threads, 5 default worker threads, which switch between those coroutines. So 1 million coroutines will be executed in 5 threads. And they will switch between the threads, and the threads will switch between coroutines as well. So that's one of the things. So they don't really allocate anything new. But how they execute is different, or rather the second part. As I mentioned, if you call a function now in your code, it will take one thread and it will keep it until it's finished. But what coroutines do is they take the thread pool and you launch a bunch of coroutines within them. And every single function doesn't have to be executed immediately. So it can be executed like 10% at a time. So it can be executed a bit, and then a different coroutine can come to the same thread and be executed a bit. And that happens until all of the coroutines are finished within those 5 threads. So that's how they're lightweight threads. They're just using threads in the background in a smart way to execute, but then don't really allocate anything.
Okay, so thank you so much.
Okay, no worries. Okay, here. We got one here. Yeah.
Thank you for your presentation. And you said that coroutines doesn't allocate the stack entries. So you have no possibility to get meaningful stack trace if something goes wrong.
Yes and no. So the stack trace is meaningful in a way that when you launch a suspension function, the actual function call within the coroutine is put on the stack. And if something crashes, the stack trace will be printed out for that function. However, it does happen, as you mentioned, so sometimes you don't get meaningful stack traces, just like, for example, in RX when you use a lot of threads. But more or less what it does is allocates one stack entry for the function call you're doing within, but it doesn't allocate extra stack entries for the coroutine itself or for the extra suspension points and execution flows. So in the example I've had with the delay function, we had one stack entry for the print some data function, right? But we didn't have an extra stack entry for the two execution flows. For the first execution flow to call the delay function and delay the suspension, and for the second execution flow to actually print some data. So in that way, they don't allocate more stack entries, but they just use one stack entry for the function call you had. What they do internally, as I mentioned, is they use the state machine of the continuation to just simply, create a stack entry. They check the label. They delay the function call as you would. So that's the delay stack entry in the function call stack, right? And then the delay returns back to that function. And what it does is the continuation says, OK, I've delayed now. I can finish and return the result. The result that will be returned will be the same function call with a different continuation. So it's simple. It's like it deletes the stack entry and puts one back in the stack. But this time it's done with different states, so different part of the state machine protocol. So what it does, it increases the label, and now it knows, OK, I've been here before because the continuation for this function exists already, and the label is 1. So I don't have to delay anything. I can just proceed with the rest of the code. And then it just goes out of the break, the case function, the case switch, whatever. And then it breaks the rest of the code, which is now the remaining execution flow, the remaining part of the function, which is the printing of the data. So in that way, they don't allocate extra stack entries, but they just reuse one stack entry, so to say. You can get meaningful stack trace. So if you try to, for example, in that piece of code where I threw the illegal argument exception, if you print that out, you will get that it happened within the coroutine, within the launch block in the main function call. So you will get meaningful stack. But sometimes, like, the compiler kind of breaks at certain points, and you may get something that is not really understandable. But I've seen this only a couple of times in some really edge cases, and that was at least a few months ago before all these new releases and updates to the coroutines API. So I would say that you would always get a meaningful stack entry, but I wouldn't be, you don't hold my word on it. But yeah.
Thank you.
Thank you for your presentation. So on one of your slides, you show how we can work in coroutines and with launch method and send the result into UI. Yep. It's work with a launch and in launch in this launch. It looks like a workaround. It looks like it's not a good piece of code. Is it really should be that? Is it really the method that you need to do to send your result in the UI?
Okay, so currently yes, but you can work around it in a way that you don't have to really use a launch block by default. You can just use some things called with context and async blocks for data data computation. What you can do is you can call different within the function call. You can call different functions which are also suspend functions. And within those functions, you can return the data asynchronously, like from different dispatchers. And then on the actual spot in your presenter, you can build an API around this, which is what I've done in one of the projects I've linked. So what you can do is build internal functions in the presenter. For example, let's name it run on UI and get data. So you would say, OK, run on UI, and it will give you the idea that you're going to do something with the UI thread. You're going to update the UI. And then within it, you can call a different function from, let's say, the interaction layer or domain layer, which will return the value for you. But how that value is compiled, you can do it in a different way. So you can do it with the dispatcher's default or IO context. And what it will do is it will know that this function is now executed in the background within the run on UI thread. So it will wait here until the value is compiled. So it will be a suspension call within that coroutine. And then you can just display it on the UI. So you can take that layer of pushing it back to the UI thread with another launch block by simply wrapping it up in something different. And of course, you can use this suspend modifier to allow you to use suspension functions within your code. And you can chain them as well. So you can have the suspension function call on the domain layer as well, and then on a different layer, on, let's say, the API layer. So you can have multiple suspension modifiers as well. So let's say yes and no. So this code is okay. It may look like it may not be really good, but it's a way to go, so you can do it like that. But what you can also do is create your own API around that, and use the coroutine scope you have in your presenter to just write an API which suits you. So it will be probably much cleaner than launching back to the main thread.
Okay, thank you.
Okay, and we have time for the last question.
Okay. Yeah.
Thanks for talks. And what about error handling?
Error handling. Okay. So people usually say that coroutine error handling is not as good as RX, at least from what I've heard. And that's sort of true. So in RX, you can handle errors in any single subscribe method you want. So you can provide an explicit method just for that subscribe, right, which will handle the errors. But in coroutines, you do it through providing the exception handlers, right? So what you can do here is just every time you launch a coroutine, you can like provide a lambda which will handle the error for this function call, this coroutine call, and then just recreate the error handlers, or maybe just use one error handler which will hold a bunch of functions together. So what you can do also is you can have one error handler which, the coroutine exception handler, my bad, which holds a list of predefined error handlers you want. So for example, for networking exceptions, or maybe read-write exceptions on the local storage, or maybe something else, something which you have internally. And then you would just, pass it down to the coroutine exception handler and switch on the correct error handler you should use. So that's one of the ways to do it. Does that answer your question? I'm not sure what you're
pretty close, but in which scope
okay.
you should put your try-catch blocks, because I knew that coroutine can crash in 3 levels of scope in coroutine. And
okay,
do
so
you know what I mean?
Yeah. So the question is, in which layer you should handle the errors? Basically, when you provide the coroutine scope, you can immediately provide an exception handler to have it like at the topmost level. But if you have something that's specific for a certain coroutine, so for example, you're doing an async block which communicates with the network, and you just want to handle those network exceptions, then you can create a new exception handler just for that. Or maybe provide a copy of the existing one, but just which handles just that exception. So you can pretty much handle the errors at any level you want. It just needs to be what suits your needs. So if it's a specific network error, then you can do it at the API call level. But if it's just general error handling, you can just push it all the way back, all the way on top of the coroutine scope.